Good evening. I welcome you all to the 10th, or sorry, ninth week of um Principles of Downstream Techniques in Bioprocess. This is our ninth live interaction session. So, without further ado, let's get into the class. So, this week we'll be looking into precipitation and chromatography. Thanks for joining, and please let me know if my voice is not audible. And in case the screen goes off, please type in the chat box and tell me. Okay, so first question. When 0.71 grams of a protein A is recovered from a broth, 0.12 gram of protein B also gets eluted with it. What is the purity in percentage in this mixture? Take a minute. Please note that we are interested in protein A and not B. So B is the impurity here. So in terms of purity in percentage, we are talking about purity of A. Any answers? Excuse me. So whenever we are asked to find the purity, what do we do? When is a substance completely pure or 100%? When you have, let's say, zero point 0.7 grams of when you have zero point 0.7 grams of recovered protein. Oops. Uh, my voice is audible, right? Did I unmute? Yeah. I'm just taking it as a random number, and all of them constitute all zero point 0.7 grams is A, then it is 100% pure, right? But here we have 0.71 grams A, 0.12 grams of B, right? So the total protein recovered is equal to 0.71 plus 0.12, which is 0.83 grams, of which A is just 0.71 grams divided by whole. A plus B is 0.83 into 100 because they've asked you in percentage. So what would that be? 0.71 divided by 0.83. So that is 85.54%. Clear? Shall we check the answer? So we are right. The answer is 85.5 percentage purity. Percent purity for A. Clear? Question 2. If the retention time of a solute is 11 minutes and the width at the base is 2.5 minutes, how many theoretical plates does the column have? So I'm just drawing the graph for your benefit, but I want you to work on the problem yourself. Now let's assume this is a Gaussian distribution. So TR equal to 11 minutes and width at the base is 2.5 minutes. So substitute into the formula and answer. Anybody? If I tell you that n is equal to 16 into TR by W the whole square, at least now, come on guys, you can do this. Thank you, Natarajan. Let's check the answer. So that would be 16 into 4.4 square Yes, I'm also getting 309.76. I mean, you generally go for the theoretical place. I mean, of course, you cannot round this off to 310. We can, of course, round this off to 309 HEDP or theoretical plates. Okay, so the answer that we got was 309.76. Moving on to question 3. With respect to problem 2 for same data, what will be the width at half maximum? So we saw this piece here, right? So in this question, if this entire height was h, then at say h by 2, what is the width at half maximum? So this is your W. So this is the entire width at the base. So what is the width at half of the maximum height of this peak? That is your question. So now we already know that n is equal to 309.76. We know that n is equal to 16 into TRI double the whole square. So this is what we used and this is what we got. What is the formula for half maximum? It's 5.54 TR by half width whole square. Am I right? Correct. So you can equate these two. Now substitute the values and tell me what. It's 11 minutes, right? What is the value of half width or width at half maximum? You need to know this relation, right? Any answers? Okay, let me work with you. 55 how that 5.54 comes. So this is an empirical relation. It's not exactly an equation. It's more of an empirical relation. So with Gaussian distributions over time, people see even the 16 is just a number, right? These are theoretical equivalent plates, or theoretical highly equivalent of theoretical plates. So you're assuming a column to be composed of multiple stages. I'm drawing a column horizontally, or you can look at it as a vertical plate where each plate is a stage where some kind of separation occurs. It's moving from one stage to another. So it is given by relation 16 into TR by W the whole square. Similarly, even for this half width, there is a relation that the sorry W half is equal to 2.35 the width at base. Sorry, 2.35 of sigma, where width at base is equal to 4 sigma. So these are just empirical relations. You can question how this came in, but over time, by seeing so many data or so many peaks, people have arrived at this number can act as a correction factor to arrive at this. That's it. And we don't have to go into the know how is a derivation of this formula, and honestly I don't know how it is derived also. I didn't look so deep into it. These were back in my bachelor's, and yeah. So for arc maximum, you have this relation put up here. Of course, you can use that formula I just told. If W is equal to 4 sigma, W half is equal to 2.35 sigma. What is the relation between these two? W half by W is equal to 2.35 sigma by 4 sigma, correct? Which would be 2.35 divided by 4, 0.5875. So W half, or here we, since we are going to substitute for W, you can take that as just rearranging these guys, 1 divided by 0.5875 is 1.7 not 2. I'm just going to go with 1.7 W half. Is that okay? Just flip this around. 4 divided by 2.35 is 1.7. So if I substitute there, what will I get? 16 into TR. Instead of W, I'm going to put 1.7 W half the whole square. What is 1.7 square? 2.89. 16 divided by, I'm taking it out of the bracket now. 16 TR square by 2.89 W half square is equal to 16 divided by 2.89 is 5.536. Happy Shriram. So probably for the not 2 and everything, it has become 5.54. I don't, there's probably a derivation for 16 TR by W the whole square also, but we are not going to get into that. So this has been approximated to 5.54 TR by half width the whole square. Fine. If you're very interested into how this derivation came through, we can take it up in the next week. So now, putting all these aside, Who has substituted this while we were talking and found out the answer here? Let's solve this one now. So 309.76 divided by 5.54 is 55.91 is equal to TR by half W, and I'm going to put the root here, is equal to 7.477, and we know that TR is equal to 11, right? So W half is equal to 11 divided by 7.477. I'm going to stop with 1.471, or maybe just 1.47 minutes. Is that what everybody is getting? Thank you, Natarajan. That's good. So yeah, we fall within the range, right? So our answer is half width is equal to 1.471 minutes. Okay, question 4. Pick out the Gaussian distribution. You've been having this question last year, this year. I mean, of course, you won't know about last year, but I think this is there in the non-graded assignment. A similar question. What is the other name for Gaussian? So I thought I'll make a pictorial options for you. So which one do you think is a Gaussian distribution? All the MCQs for the day are very simple, straightforward. Please participate with the options in the chat box. So which one is a Gaussian distribution? Gaussian is also called normal distribution. Think- Thank you, Urja. We just saw a distribution like this, right? And I just called it Gaussian. The thing about Gaussian is that it is symmetric about the center. That is, the left and right arms are equally away from the center of the peak, right? And the highest concentrations or the greater numbers come towards the center of the peak and wane away symmetrically. Okay, so it's these are examples of non-Gaussian distributions where you have a positive or negative skew. We called it fronting and tailing, I guess, in the lectures, and this is a bimodal distribution, which means you have two modes. Modes is where you have repeats, right? Repetition. So there are two things that are or how do we put it, there are let's say in a population you have two species that are equally popular or equally, this is not equal but most popular. Let's say you have a number of junk food, and if two of them are more popular, you will have something like this than the others, right? Two competitors in health drinks over the others, something like that. Here it's probably two proteins eluting out, but they're overlapping with each other's distribution. There's no proper resolution if we are talking about a chromatographic distribution or a illusion of protein. Here there's no proper resolution. In these regions you're going to have both protein A and protein B eluting together. Okay. So the right answer, as Urja pointed out, is option B. Moving on to question 5. Plate height in a chromatography can be increased by, remember, increased. Option A, reducing particle diameter in the matrix. Option B, reducing column diameter. Option C, reducing thickness of the liquid film. And option D, increasing flow rate of the mobile phase. Let's take a minute. Please try to answer. It's no crime if it's wrong. Any answers? Okay. First of all, plate height, like we just discussed, if you have a chromatographic column, we are talking about, uh, at least theoretically, we are splitting the chromatographic column into so many theoretical plates where each is a stage. Thank you, Urja. Right? So, between these stages, you're expecting some kind of separation or purification to take place. And plate height, the smaller the plate height, better is the resolution, separation. The peaks are going to be sharper. Correct? The efficiency is going to improve. Purity is going to be better because you have better resolution. Right? So the height of theoretical plates is desired to be low, which means you're having so many tiny stages before it comes out. So it gives it a lot of opportunity to separate. Correct? Chromatography is an analytical as well as a separation technique. So the smaller it is, the better. So how do you reduce the theoretical plate height? By reducing particle diameter. That's a good way of, that's one method, but still it will increase the pressure. Again, column diameter reduction is another way of reducing the plate height. Reducing thickness of liquid film. Please note that everywhere we are trying to uh, improve the mass transfer. Correct? Although you call it chromatography, solid gas, or liquid gas, at the end of the day, we are talking about molecules, chemicals, protein species moving between one phase to the other. from one bulk phase into the other one, or the mobile phase, which is trying to elute the protein or separate the components. So the thickness of the liquid film all play a role in how fast or how quickly the mass transfer can happen. So reducing thickness again helps in decreasing the height of theoretical plates. But increasing the flow rate of mobile phase makes it very quick. So if you're going to go very quickly through all these plates, you're not going to enable separation to the maximum possible level, right? Rather, decreasing or reducing the flow rate, a slow flowing chromatographic column is going to be better at separation than a fast moving. I mean, we are not talking about the entire column moving, it's just that the mobile phase, the flow rate of the mobile phase, if it's slower, separation is better because you're giving it more time to interact with the stationary phase. Correct? Therefore, increasing the flow rate goes to increase the theoretical plate as asked in this question. So option D, as Urcha pointed out, is the right answer. Okay, I hope that was clear for everybody. Moving on to question 6. Two peaks have retention time of 5 and 7.5 minutes, and their corresponding width at the base is 2 and 3.5 minutes respectively. What is the resolution of the column? Again, take a minute. Remember, I'm just waiting for your answers. So continue with solving the problem. Any answers? Okay, at least are we familiar with the formula? Let me give up. Last time. Okay, let's see what the formula is. Resolution is given by delta retention times the difference in retention times by average of width at base. So that would be tr2 minus tr1 divided by wb1 plus wb2 whole by 2. So this would come to the numerator, right? So 2 into tr2 minus tr1 divided by wb1 plus wb2. Substitute this and tell me the answer. Yeah, I'm going to be satisfied with that. So this is 3.5 and this is, oops, I guess you can't do a control Z here. Yeah, this is 2 minutes. Substitute 2 into, nobody answered. 7.5 minus, thank you Natarajan, 7.5 minus 5 divided by, thank you Urja, base is 2 plus, thank you Nisha. Great, good to see everybody solving. So 7.5 minus 5 will be 2.5 into 2 is 5 divided by 5.5, correct? Oh, 0.9, not 9, I'm going to go with 0.91. Okay, so this is your resolution. Let's check. Yes, so the answer that we have is 0.91. Going to question 7. For the two peaks mentioned in problem 6, what is the average width at half maximum? Okay, so they're asking you this, and we derived something, right? This one here, I think we can use this, right? Why don't we use this? And but they're asking about average. Okay, let's solve this with two methods and see where this goes. So w is equal to 1.7. It was 1.7, not 2, but let's go with 1.7. W half. W is equal to 1.7. So W1 is equal to 1.7 blah blah blah. Okay. This time since we need half, why don't we go with this? So half is equal to 0.5875 into W, right? Let's use this also. Half of 1 is equal to 0.5875, correct? Of W1. So what did we have? Peak at 5 minutes. 7.5 minutes. This was PR. W was 2 minutes and 3.5 minutes, correct? I just do the number line. Yeah. 5, 7.5 to 3.5. So this will be your 1 and that will be your 2. So I'm just winging with this. I have not solved this way, but since we derived that today, not really derived, let's just try with this relation. If this doesn't work, we'll go with the conventional formula. So what do we have here? So half width 1. Should I call it A or something? Maybe that's better. Let's call this A. Whatever it is, it's still weird. Huh. This 0.5875 into 2 minutes, correct? 1.175. Similarly, half of B is equal to B or 2. Maybe I'll just stick with 1 and 2 because I've written it there. Point 0.5875 into W2, which is 0.5875 into 3.5 is 2.056. I'm going to stop with 0.56. So they've just asked average width at half maximum. So what will be the average? W half of 1 plus W half of 2 by 2, right? So I'll be having 1.175 plus 2.056 by 2. So I'm getting 1.6156. So I'm just going to round it off at 1.62. That's a huge round off. Tell me if you get the same. Plus 2.06. Now, traditionally, we have this relation R is equal to delta dr by average width at base, which is also equal to 0.589 delta t and average of half width. You already know that this value is 0.91, which gives us, so I'm doing the second method here. I hope everybody is clear till that extent. I have stopped this particular process here. I'm going to just check if both of these match. So here what do we have? 0.91 by 0.589 is equal to delta t is 2.5 by half, which gives, I don't want to mix things up, so I'm going to rewrite this however childish that may be, into 589. I hope I didn't mix things. Yeah, 2.5 into 0.589 divided by 0.91. Okay, we're getting 1.618, which I'm going to approximate into 1.62 minutes, which is the same as this. Was this clear? Have I confused anybody now? So I have derived this or this from W is equal to 4 sigma and W half is equal to 2.35 sigma. So based on that we have arrived at these relations and we are getting the same answer with both methods. This is the actual formula that you need to use. So the answer that we got was 1.62 minutes was average, right? Yeah. Was that clear? No questions, right? We are moving on to question 8. You have a similar question in probably non-graded assignment, I guess. Three proteins A, B, and C have neutral, negative, and positive charges respectively. What will be the order of elution in an anion exchange chromatography? Remember that anions are getting exchanged. So I expect option A, B, C, D, E. You have 5 options. Guys, any thoughts? Okay, so when you're having anion exchange chromatography, anions are going to be exchanged. Cations are positive, anions are negative, right? So if anions have to be exchanged, the matrix has to have positively charged species, correct? So this is present in the column itself. So now negatively charged species interact with the stationary phase. This is how anions are going to get exchanged. So whenever the mobile phase is more negative, then the negative species in the mobile phase is exchanged for the already bound components of the mixture inside the column, correct? So if I'm having, let's say, other positively charged species, they're going to get repelled, correct? Yes or no? So obviously they are not going to bind to the stationary phase, and they are not even going to interact with the stationary phase. So whatever is positive is going to spend the least amount of time into the column, correct? So whichever is positive will come out first, followed by mm, let's say something is neutral, it's neither positive nor negative. It is not going to be repelled by the stationary medium, stationary phase, but again it's not going to be attracted also. So what happens? These leave next, and finally the negatively charged components are going to come out. For want of space, I'm putting them really close together, but if the column is well resolved, there's going to be some time gap between each of these species. So we have one thing clear: positive followed by neutral followed by negative. So what is what here? A, B, and C. C is positive, B is neutral, A is negative. So what will be the order of illusion? First, the positives are going to come out. So whichever has C is the shortlisted option, only one here, followed by neutral. What will be the order of illusion and anion exchange? So anions are going to come last. Great. Ha! Nobody pointed this out. Neutral, negative, and positive. This is neutral, this is negative. So C is your first option, followed by neutral, which is A, followed by negative, which is B. So CAB is the right answer. Clear? A very straightforward question only. Moving to question 9. The first kind of species to elute from a gel permeation chromatography would be, again straightforward question, small molecules, cations, big molecules, anions. Let's take half a minute. A, B, C, or D? Guys, Urja, Natarajan, Shriram, Nisha, others were there in this call. Gel permeation chromatography is just another name for size exclusion chromatography. Maybe the color is not the right choice. Is it visible? Should I write again? Size exclusion chromatography. Gel filtration chromatography. So everything is talking about size, filtration, sieving, right? So it is definitely not about cations or anions. So what is it, big or small? So if you have a column and it is filled with beads, okay, and these beads are going to have pores in them. So in a cross section, it's going to have so many pores in them, right? Throughout the spheres, they're going to be tiny pores. Now, if the molecules are small, they're going to go and spend some time in the pores before the elution medium can actually, or the mobile phase can bring them out, right? Whereas the ones that are bigger, they will not be able to go into the pores at all. There will be some that can barely go in, very tiny ones that will spend even more time inside. right? So based on the size, the biggest species are going to come out first, followed by some smaller species, followed by even more small molecules. Finally, the extremely small molecules, right? The bigger the particles, faster they elute outside. So, the first kind of species to elute from a gel permeation chromatography would be big molecules, right? Okay, last final question. The volume of pores and space present between the stationary phase, which is filled by the mobile phase and column chromatographies. So again, you have one more column chromatography problem. So if this is your column and this is your packing material, there is bound to be some space, right? I'm just talking until you figure out the answer and type in, which doesn't seem to be happening. But yeah, I'm just taking a cross section here. So the volume of pores and space, excuse me, between the stationary phase, whatever pores or space, even in if this is a gel permeation thing, then you're going to have pores also. So these pores and any space between the packing material, between these beads or any other material or synthetic polymers. So whenever the mobile phase comes in, it's going to fill these pores, these gaps between the stationary phase, interact and then come out. Right, this is the space that's actually the volume that's actually filled by the mobile phase within the column chromatography. So what is this volume called? Is it elution volume, bed volume, retention volume, or void volume? Think about each. Bed volume is the entire volume, including stationary plus mobile phase. So if this entire column were packed from this end to this end, the volume of this particular cylinder will be the bed volume, including the pores, including the space, whatever is there. Elution volume, on the other hand, speaks only about the mobile phase and the amount of mobile phase required to elute a particular compound. So the elution volume for protein A will vary from elution volume of protein B or elution volume of some other component C, some salt D. Right, different components have different elution volumes for the same column. But let's say if there is one particular compound which does not bind in the column at all, so the minute it is introduced here, it does not bind, it just comes travels along with the elution volume and comes out of the column at time t at volume v. So for this particular compound, elution volume will be equal to the volume of pores, right? Because the mobile phase is just filling these gaps and coming out. Please remember that it is there throughout. I just took out a specific area, but yeah, throughout the bed you're having the packing material. Right, elution volume will be equal to the pores or voids within the column of the stationary material packing. So this might be right in certain cases, but it is not necessarily equivalent, because for each compound you have a different dilution volume. What is retention volume? The time taken or the volume required for a particular uh, um, compound. How much time or volume it is retaining within that particular chromatography column. So you see TR. So the volume of elution mobile phase you get at TR will be VR, retention volume. So again, that is not your answer. It is the void volume, which describes the volume of force and space between the stationary phase, which is filled by the mobile phase in column chromatography. Okay, elution volume can be equal to void volume when there is a particular compound which does not interact at all with the stationary phase and just comes out the way it entered immediately along with the mobile phase. Then in that particular case the elution volume of that particular non-interacting compound is equal to the void volume, but not always. I hope that was clear. In case there's anything else you want me to repeat or clarify, you can tell me now. I hope this session was useful. There's nothing more to add. Okay, then let's close it down. Thank you all for joining. See you next week.